This program is brought to you by Emory University.
Okay, good morning. How are you all doing today? Okay, so starting tomorrow, you will be able to pick up your exams on the second floor of Atwood in the bins by the labs. And so your exams will be located there, placed alphabetically by your last name, and within such bin, you can locate your specific exam by your 4-digit code in order to protect your privacy. Okay, today we're going to continue to talk about Chapter 7. The last time we looked at the valence bond theory, and we were considering the hybridization of the different orbitals in conjunction with the valence bond theory in order to account for bonding in some of the main group elements. In particular, we focus more so on the elements of the second series, the main group elements of the second series, being central atoms forming compounds whereby the hybridization of the atomic orbitals more suitable as far as forming these hybrid orbitals, which, when overlapped by valence bond theory with the orbitals of the peripheral atom, leads to structures of molecules that are consistent with the experimental observed bond angles for those molecules. And so, this is a rather distinction, another distinction of these second series elements, like we've considered so far, relative to heavier elements, atoms of heavier elements, larger principal quantum numbers, and in this case, in terms of the valence bond theory, comparing hydrogen sulfide with compounds of carbon, sulfur, central atom being of the third row, and carbon, in this case, being of the second row, whereas the less adulterated, less hybridized, pure orbitals for the sulfur central atom resulted by the valence bond theory in orbitals suitable with experimental observed bond angles in hydrogen sulfide. The pure, unadulterated, unblended orbitals of this second series element, carbon, like we talked about last time, when overlapped by valence bond theory with peripheral hydrogen atoms, such does not result in molecules consistent with observed molecules between carbon and hydrogen, as in methane, like we talked about, where the bond angle is actually 109.5 degrees in methane, and the carbon bonds 4 hydrogens. Unlike the prediction of the valence bond for the pure 2s and 2p orbitals of the carbon, whereby the theory predicts 90-degree bond angle and a molecule of C sub H2, or rather CH sub 2. And so we were able to explain this last time based on the need to mix those 2s and 2p orbitals of this second series element carbon, and mixing 4 of those atomic orbitals, forming these hybrid orbitals, and thereby quantum mechanics by the hybridization of these quantum mechanical S and the 3 p orbitals of the p subshell. In this way, the quantum mechanics counts the shape such that linear combination of these thereby the counting of these orbitals, results in, based on the phasing of the S relative to the 3p, results in these 4 hybrid orbitals. Counting, summing those orbitals, result in these 4 hybrid orbitals. And also the summing results in a counting of these orbitals such that the relative angle between these hybrid orbitals is 109. And thereby, the quantum mechanics actually, in counting by this linear combination, it calculates the correct bond angle and shape of the methane molecule, this second series carbon central elemental example. And it's important to note that, how the quantum mechanics quantitatively, by such hybridization of the atomic orbitals, it calculates the geometry of the molecule. That's important to note and to understand and to contrast relative to what you did in the prior chapter when you rationalize such bond angles qualitatively, right? Based on the valence shell electron pair repulsion theory. In the prior chapter, valence shell electron pair repulsion theory, you reason qualitatively such bond angles. But in this more advanced valence bond theory, based on the quantum mechanics, and the quantum mechanics of hybridizing those orbitals, the quantum mechanics calculates, okay, the shape of such molecules. So I felt it very important to emphasize that. And furthermore, just as we can hybridize in some molecules S and 3 of the P, we can hybridize in other molecules S and 2 of the P, depending on the composition of the molecule and the electronic configuration of the atoms for the elements in the particular molecule. For example, such often occurs in molecules containing elements with central atoms of carbon, nitrogen, and oxygen. May involve hybridizing the 2s orbital with 2 of the p orbitals rather than 3 of the p orbitals. And so by doing, we see in this particular hybridization, the quantum mechanics calculates shape of molecules such that the bond angles are 120, in contrast to what we did in the last chapter by the valence shell electron pair repulsion theory. We qualitatively reason such bond angles in the quantum mechanics based on the hybridization of these quantum wave functions, linearly adding them, thereby calculating. We end up with these mixed hybrid orbitals, blending them mathematically, calculating the hybrid orbitals, and the resulting bond angles between those hybrid orbitals reflect the calculation of this kind of shape for such a molecule containing central atoms, which blend 2 of its p orbitals, say 2px, 2py, and 2s orbital, resulting in 3 hybrid orbitals with calculated bond angles of 120 degrees. And so as we consider bonding, between the elements based on the valence bond theory, it's important that we realize the quantum mechanics is further predicting 2 types of bonds, distinguishing possible bonding based on the geometry of the overlap. Like we were considering the last time, based on the quantum mechanics in the resulting wave functions and orbitals on the atoms involved in the molecule, these atoms may be approached to form the molecule such that these quantum orbitals, they overlap, and the overlap region is between the nuclei of the involved atoms, and the resulting overlap based on the valence bond theory, where the overlap of the atomic orbitals is between the nuclei, and therefore it is along the same axes or plane containing the nuclei. Such overlap results in sigma bonding. This second type of bonding can occur. Pi bonding, it can occur when the geometry is such that the overlap of orbitals is off the internuclear axes. And so we can see examples of sigma and pi bonding in a molecule, say, involving a px on the two atoms as the nuclei are approached in forming the molecule. The wave functions of px symmetry on the two atoms, they overlap, and they overlap between the two nuclei. Actually, I found the pointer. I had asked for it. And so this is the basis of sigma bonding, right? The basis of sigma bonding. Because this overlap region, it exists in the same plane and along the same line as the two nuclei, where the two nuclei are at the nodes here for these two p sub x orbitals. On the other hand, for pi bonding, maybe we could consider on these atoms the pz and the py orbitals, which are perpendicular to the px, you recall. And so as these atoms approach, it may be possible that these perpendicular orbitals may overlap in a region not involving the plane of these nuclei. See, here's the plane involving the nuclei. But if these two atoms are pushed together to form some molecule, the overlap region may be in a different plane, above and below the plane containing the nuclei. And such overlap is the basis for the pi bonding. So it's important to make that distinction. It's important also to consider, which we will in the next couple of slides, that based on this type of bonding, pi bonding, the rotation of the atoms about the internuclear axis would cause a breakage of this bond, right? If we took, say, these two atoms and rotated about the z-axis, we rotate one of the atoms relative to the other about the z-axis, then that would break the overlap, breaking the pi bond. And so molecules having pi bonds, the pi bond presents a barrier to such rotations, such bond rotations. Okay, so we can consider this in this molecule dichloroethylene. In comparison to dichloroethane. So on the left here, this molecule dichloroethane, it has a carbon-carbon sigma bond. On the right here, the molecule dichloroethylene, it has a carbon-carbon double bond involving a sigma, well, of course, the sigma between the hybridized S and 2px and 2py, and a pi bond can form by the overlap of the pz atomic orbitals, unhybridized atomic orbitals on the two carbons. And so that pi bond in the ethylene, dichloroethylene molecule here, it would restrict rotation about this carbon-carbon bond, right? Because the rotation would break that pi bond. And so it would take energy in order to break that pi bond. And so depending on the conditions, under lower energetic conditions, this molecule would be irrotational about that carbon-carbon bond. On the other hand, comparing to the carbon-carbon sigma bond, having no pi bond, there is no or much less restriction to rotation about the carbon-carbon single bond. And so it is like free rotation can occur about the carbon-carbon sigma bond. So this results in different energetically possible orientations of the chlorines in the peripheral atoms due to the relatively free rotation about the carbon-carbon single bond there. But the carbon-carbon double bond, it sort of freezes the molecule into two possible relative forms. One form where the chlorines are on the same side of the double bond, and another form of this molecule called an isomer, where the chlorines are on opposite sides. And so this is the pi bond prevents rapid transformations between these two isomers. So under low energetic conditions, or possible conditions, these two different isomers can exist, and they don't interchange because the pi bond prevents their inner transformations. And so based on the different structures there, these two molecules have different properties, right? These are isomers. They have different properties. So it's quite interesting to compare such, because typically, so far in the course, we've only considered variation in properties of molecules because they vary in their composition or they vary in the skeleton of how the atoms are bonded together. But here's an example of a molecule where the skeletal structures are the same, yet there are two different forms exhibiting two different properties, right? And this results because the pi bond restricts rotation about that carbon-carbon double bond. Okay, so also we can consider examples where the central atom would involve blending of one of the P with the 2s, and this results in sp hybridization. Okay, and so the hybridization of such, a good example of that is in this molecule acetylene, and I know you can't jot all of that information down. And like I've done with the other chapters, this chapter is going to be posted on Blackboard. Also tonight you're going to get a post on Blackboard for homework for this chapter. And so we will finish up a great deal of Chapter 7 today, and on next week we'll start looking at Chapter 8. Okay? So the next class you can start preparing as far as possible clicker questions in Chapter 8. Okay, so in this molecule, acetylene, it contains 2 carbons and 2 hydrogens. And such molecule, based on its Lewis structure, has a triple bond. And so using the valence bond theory, we can, as we did with methane and ethylene, consider for such carbon, 2 carbons, and 2 hydrogens, the central carbon atom involved in bonding between 2 atoms, a hydrogen and another carbon. And so we can consider, based on the energy diagram for the central atom, the carbon atom, its electronic configuration, having 2s and 3 2p orbitals, and based on the number of atoms in that Lewis structure and the number of bonds involving the central carbon atom, 2 electron groups, one with hydrogen and one with the other carbon, we can consider by the valence bond theory hybridizing 2, therefore, atomic orbitals in order to form those 2 electron groups for bonding the hydrogen and bonding the other carbon. And so thereby, this is how the sp hybridization results. For the other 2 examples, the central carbon was involved in 4 bonds and 3 bonds, thereby requiring 4 electron groups and 3 electron groups. Therefore, we hybridize the S with all 3 of the P for the 4 electron groups, and in the case of the ethylene, hybridizing the S with 2. In this molecule, based on its composition, ethylene, we need 2 electron groups, and so we only hybridize the carbon with the 2s of the carbon with 1 of the P. And so by doing, we form 2 hybrid orbitals. The quantum mechanics, by blending the wave functions for the S and the P, it counts these 2 hybrid orbitals. And so it's important that you consider in the simpler case here involving the s and the p. The p orbital, the s orbital has only one phase. It's positive. The p orbital, its wave function has a positive and a negative. The phasing has a positive and a negative lobe. So in combining these two, in summing, summing these two, you end up with one hybrid where the positive S constructively adds to the positive P on one side to form a larger, fatter lobe, and it destructively combines with the negative lobe for this P wave function, so that there's a diminish, right? A diminution of the size of the lobe. And this other hybrid orbital, it is formed by subtracting the P from the S rather than adding the P to the S. And so thereby you're counting these two quantum mechanically, and you're calculating quantitatively these two orbitals. So I go into details there because it's easier to sort of visualize such constructive and destructive combinations for the SP hybrid. Rather more involved when we consider three-dimensionally combining the S with three of the P. But likewise in those cases. Okay, so using this hybrid orbitals, those two hybrid orbitals about the central carbon, by the valence bond theory, you overlap the hydrogen with one of those, and you overlap the other carbon with the other hybrid orbital to form two sigma bonds. One sigma bond to the hydrogen by this central carbon, the other sigma bond to the other carbon. However, you recall, based on the electronic configuration for the carbon, there were two other p orbitals, and they contain lone electrons. And so these carbon atoms, each having lone electrons in those 2py and 2pz, they can approach closer in space so that the 2py and 2pz orbitals overlap, and the overlap is off the internuclear axes. And these two overlapping 2py and 2pz, right? 2py and 2pz, they form pi bonds. And notice, by so doing, the two carbon atoms have to compress closer together. And the quantum mechanics is thereby not only predicting the pi bond, distinguishing the sigma from the pi bond, the quantum mechanics is quantitatively explaining the bond length. Because in the prior chapter, you learned that the single bond is longer than the double bond, and the double bond is longer than the triple bond. And so quantum mechanically, this is calculating the shorter bond length of the double bond and the even shorter bond length of the triple bond, because these carbon atoms have to pull together more closely. The bond length has to be smaller in order go ahead. The bond length has to be smaller in order for significant overlap of those 2px, 2py, and 2pz. Right? But energetically, the sharing of electrons off the internuclear axes lowers the potential energy. And the quantum mechanics is also calculating the greater bond energy of the double bond relative to the single bond, and the even greater bond energy of the triple bond relative to the double bond. Okay, so based on consideration of this hybridization, you can consider this question concerning hybridization of carbon and carbon dioxide, right? Carbon dioxide is a rather stable molecule from combustion of one of the stable molecules from the combustion of hydrocarbons. When hydrocarbons like methane or acetylene, like we just considered, when they combine chemically with oxygen, they form carbon dioxide and water, right? And these reactions, they release a lot of energy, right? This is the basis for internal combustion engines. These reactions are very exothermic. And you recall, you can calculate energies of reactions, approximate them based on bond energies of reactants and products. And so you can understand the lowering of the potential energy in forming carbon dioxide based on the bonding in the carbon dioxide. And the bonding in the carbon dioxide depends on the hybridization about the central carbon atom. Right? So what is the hybridization of carbon in this carbon dioxide? Okay, so most people should have calculated, entered their answers. So you take another 30 seconds. So we have to move on. Okay, so the correct answer is A. Okay, so not only does the quantum mechanics explaining the geometry of these linear molecules, trigonoplanar molecules, tetrahedral molecules, typically associated with the second series elements being the central atom. For the heavier elements, main group elements, the quantum mechanics also accounts for those which don't obey the octet rule, involving expanded octet, and by hybridizing S and P with d orbitals, quantum mechanically, one can form hybrid orbitals, and these hybrid orbitals calculate in the linear combination to form them, such that these bond angles arise, right? Bond angles of 90 degrees and 120 degrees in trigonal pyramidal, electron domain geometries, and such can arise by mixing an s orbital with 3 of the p orbitals and a d orbital, a suitable d orbital. And so you recall from the prior chapter that this such hybridization not seen among second series elements, but such hybridization and such consequent bond angles and expanded octet sometimes occurs for those elements of valence shells having principal quantum numbers greater than 3. And this is so because for such valence shells of principal quantum numbers greater than 3, those subshells have D, low-lying D subshells. And so this can result in hybridizing the S and P orbitals of that subshell with that low-lying D, forming hybrid orbitals thereby. So this also points out that orbitals that are closer in energy, they tend to more ably mix to form hybrid orbitals contributing to molecules, right? Orbitals that are very different in energies don't tend to blend to form hybrid orbitals, right? So although there are d orbitals in these atoms of the second series, having valence shells of the second series, those d orbitals are very high in energy relative to the second shell. And so because of the large energy disparity, you might wonder, well, why can't I mix 2s, 2p with 3d? There's large energy difference. And so because of such energy difference, energetically, such hybrid from 3d with 2s and 2p, right? It's not energetically going to contribute to bonding to form a molecule. Okay, so likewise, we can consider hybridizing for these post-second series elements, elements having valence shells of principal quantum number 3 or larger. We can consider mixing their S and P subshells with 2 of the D orbitals. And this kind of mixing forms hybrid orbitals. And the quantum mechanics for such mixing, hybridizing S subshell with P subshell with 2 orbitals of the D subshell, it results in a geometry consistent with 6 hybrid orbitals of high symmetry with 90-degree 90-degree angles between all 6, which is, of course, the octahedral geometry. Okay, so in summing up, how do we in general use the valence bond theory in order to model the molecule? First, we draw the Lewis structure, right? Then, using from the prior chapter, using the valence shell electron pair repulsion theory, with that Lewis structure, you can predict electron group geometry about the central atom, right? And then in this chapter, based on the valence bond theory and hybridization, you can select a hybridization scheme that matches the valence shell electron pair repulsion theory, like we were considering in prior slides. And then you can sketch the atomic and hybrid orbitals on the atom in the molecule, right, showing the overlap of these orbitals on the central atom with the overlap of the orbitals of the peripheral atom. And notice in this class, we only consider hybridization of orbitals on the central atom, right? Okay, so what I want to do next is to note some limitations of the valence bond theory, and the latter part here we're going to start looking at the more advanced theory that addresses the limitations of the valence bond theory. This more advanced theory is the molecular orbital theory. So what are the limitations of this, some of the limitations of the valence bond theory? Well, it's quite successful, like we've noted, in predicting properties better than the Lewis theory. And it distinguished two types of new bonds and explaining bond lengths and bond strengths. But recall, early in the chapter, we noted the magnetic behavior of the oxygen molecule. When we use the valence bond theory, we're not able to explain this magnetic behavior of the oxygen molecule. Also, in using hybridization, we tweaked the valence bond theory so that it better accounts for the geometry of many molecules, right? Because using pure atomic orbitals, the valence bond theory fails to explain the shapes and geometries of many molecules. Okay, so part of the reason why the valence bond theory has these inadequacies, well, it is a greater success than the foundation, the Lewis model, because it incorporated quantum mechanics, right? But part of its inadequacies and limitations is that it insufficiently incorporates quantum mechanics, right? And so the quantum mechanics in the valence bond theory, it is included by using atomic orbitals of the atom in the molecule. And so there is some incorporation of quantum mechanics, but the incorporation is rather an approximation where the molecule by valence bond theory is approximated and described by the quantum mechanics of its atoms. A better way of incorporating quantum mechanics in the molecule is to quantum mechanically model the whole molecule. And this is what molecular orbital theory does. Okay? Okay, so the molecular orbital theory, unlike the valence bond theory, it applies the Schrodinger wave equation to the whole molecule, as opposed to applying the Schrodinger wave equation to the individual components, the atoms in the molecule, and then constructing bonds from those atomic orbitals, right? That's what the valence bond theory does. It applies Schrodinger's equation to the individual atoms, and the resulting wave functions it uses to construct bonds to describe the molecule. On the other hand, molecular orbital theory, it applies the Schrodinger equation. Recall the Schrodinger equation. I write here on the board the Hamiltonian on the wave function being equal to the energy times the wave function. And molecular orbital theory applies this equation to the whole molecule rather than the individual atoms in that molecule. And it derives wave functions characteristic of the whole molecule. Right? And so, by so doing, the molecular orbital theory results in very complicated Schrodinger equations, which are very difficult to solve mathematically. Right? And so what is done is to consider the resulting Schrodinger equations and obtain approximations to exact solutions. Okay, so how does the molecular orbital theory how does it do so? How does the molecular orbital theory apply to the whole molecule? Maybe we consider and contrast. Oh, here we go. This may not work. Oh, it does. A little. Maybe we consider and contrast the H2 molecule by molecular orbital theory relative to valence bond theory. So So by the molecular orbital theory, we find the Schrodinger equation for the whole molecule. So maybe I consider here molecular orbital theory. And I consider on the other side here the valence bond theory. And so for this hydrogen molecule, we obtain Schrodinger's equation for the whole molecule. And we're not going to write that out, of course. But like I was saying in the prior slide, such Schrodinger's equation for this molecule is extremely complicated and difficult mathematically to derive and solve exact solutions for the wave functions. And so what is done is to find approximations to the exact solution. And then we can judge those approximations, right? So, in other words, we give some educated guess concerning the molecular wave function that would be a solution to Schrodinger's equation for the whole molecule. And then, in order to judge the guess, we use that wave function, that approximation, to calculate the energy of the molecule. And then we, based on the judging, determine whether the guess is a good guess or a poor guess, based on how it minimizes the energy of the molecule, right? Okay, so one of the simplest and most useful initial guesses for approximating the wave functions in molecules is to use what is called a linear combination of the atomic orbitals, right? Linear combination of atomic orbitals. And so, so what is a linear combination of atomic orbitals? This is a weighted mixing of the atomic orbitals linearly, a weighted mixing of the atomic orbitals of the atoms in the whole molecule, right? And so by doing so, we can say, well, the wave function for the molecule will be some linear combination of the wave functions, in this case, for the atoms in the molecule. A blending of the atomic wave functions of the atoms, somewhat in analog to the blending of the atomic orbitals of an individual atom for forming hybrid orbitals of that individual atom, right? So it's sort of analogous. It's a weighted summing of atomic orbitals of the different atoms in the molecule relative to the weighted average of the atomic orbitals of the central atom right, as we did for hybridization, right? So pictorially, we can consider the atomic orbitals in the hydrogen molecule, the two hydrogen atoms, and the ground state wave function would be 1s. And so we could find, by the molecular orbital theory, the wave function in the molecule by linearly combining these atomic orbitals for the two hydrogen atoms. In this case, the ground state atomic orbitals, the 1s. So we blend 1s for hydrogen A, 1s for hydrogen B, right? And there are two possible combinations linearly. We can add those two atomic wave functions to approximate a molecular wave function, or we could subtract those two atomic wave functions, right? And so in the first case, if we linearly combine by adding, based on the nature of the phasing for 1s atomic orbitals, we get constructive product. We get constructive interference between those two atomic wave functions, right? Because the 1s is positive. On the other hand, if we sum negative, if we add the 1s of one plus the negative of the 1s of the other, then we destructively blend those two atomic orbitals, and we form a molecular orbital known as the antibonding molecular orbital. Right? So this is sort of pictorially an illustration of how molecular orbitals are approximated from atomic orbitals by the linear combination of those atomic orbitals. Right? And in the linear combination of the atomic orbitals, in forming the molecular orbitals, the number of molecular orbitals that are produced from the linear combination is equal to the number of atomic orbitals that are blended. In this case, we blend two of the atomic orbitals. So there are two possible molecular orbitals that can result. By the constructive blending, we form a bonding molecular orbital. By the destructive blending, we form an antibonding molecular orbital. Okay, so let us consider why this first case here of constructive combining the atomic orbitals results in the bonding molecular orbital. Okay. So the bonding nature of this molecular orbital, you may understand based on such constructive interference of those wave functions, and those wave functions reflecting the probability of the electron for those two atoms, right? If the blending results in constructive summation of those wave functions, that means that the electrons, based on the square of this molecular orbital, are they have a greater probability of existing in this region in the molecule, right? And so such greater probability, in particular between the two nuclei, for the electron's existence in this molecular orbital results in the electrons of that molecular orbital binding those two nuclei. On that basis, such molecular orbital lowers the energy, and it contributes a bonding molecular orbital. On the other hand, the linear combination that destructively interferes those atomic orbitals, such that the destructive interference causes zero probability between the nuclei, and you recall from prior quantum mechanics, such regions where the probability is zero, these are referred to as nodes, right? Why are they nodes? Zero probability of the wave functions, in this case the molecular wave functions. That means that there's no probability that the two electrons or electrons exist in this region with any motion. And so if no electron is existing in the space and with motion between the two nuclei, then there's no negative charge to bind the nuclei. And so such molecular orbital is therefore antibonding. Excuse me? Excellent question. How do we contrast this to valence bond theory? And so in the valence bond theory, we consider the atoms and their atomic orbitals, and we bring those atoms together such that the atomic orbitals on the atoms overlap, and that overlap region results in bonding. Recall by the energy diagram, right? We bring the atoms together, and as we bring the atoms together, the atomic orbitals on the two hydrogen atoms overlap. Yes. Okay, so based on the molecular orbital theory, electrons in bonding molecular orbitals are stabilized because the energy is lowered. On the other hand, electrons in antibonding molecular orbitals, they're destabilized, right? Based on the node between the nuclei, like we just considered. Okay, an important property is the bond order. As we consider the molecular orbital theory. And so this is a new concept you should make note of. The bond order, this is a quantity that's equal to 1/2 the number of bonding electrons minus the number of antibonding electrons. Okay? In calculating the bond order, you only need to consider the valence electrons. And the bond, it's important to note the bond order may be a fraction. Higher bond orders, they express stronger and shorter bonds. Okay, if the bond order is 0, then this suggests an unstable bonding between the atoms. Right? In terms of magnetic properties, a substance will be paramagnetic if the molecular orbital diagram, it has an unpaired electron. On the other hand, if all the electrons are paired, then it's paramagnetic. So let's look at the molecular orbital diagram for the hydrogen molecule like we've just done, and let's configure the electrons in the molecule. Like we configure the electrons in the atom, right, to find electronic configurations of atoms. Let's configure electrons in molecules based on bonds that form between valence electrons of the atoms of those molecules. And so, like we just considered, the molecular orbital theory determines from those atomic orbitals of the valence shell of the atoms in that molecule, molecular orbitals. How? By linear combinations of those molecular orbitals. Okay? And in the linear combination, we'll see the energy as well as the symmetry of those atomic orbitals determine which atomic orbitals have more important linear combinations. Okay, in the case of the hydrogen molecule containing 2 hydrogen atoms, thereby 1 electron each in the valence shells of those 2 atoms. Combining those orbitals of the 2 atoms, their valence shells, 1s for each, it results in 2 molecular orbitals, 1 bonding we noted, and here's the orbital diagram for such, the other one antibonding, and we can configure the valence electrons among those molecular orbitals just as we configured the valence electrons among the atomic orbitals for the individual atoms. We configure the electrons by Aufbau principle in order of increasing energy. We configure the electrons in the molecular orbitals based on Pauli's exclusion principle. And also, we configure the electrons in the molecular orbitals in the molecular energy diagram based on Hund's rule. And so, based on the Aufbau principle, the 2 molecular orbitals that we form for the hydrogen molecule, okay, we have a couple of more minutes, just make note. The one of lowest energy is the bonding molecular orbital. And so, by the build-up principle, the Aufbau rule, we will place the 2 valence electrons in this lowest energy orbital. And this would determine, by Pauli's exclusion principle, they would have to have opposite spin in that bonding molecular orbital. Right? And this would be the configuration the electronic configuration for the molecular orbital of the hydrogen molecule, right? This would be its ground state, okay? Okay, so the Bund order for such, how would you?
The preceding program is copyrighted by Emory University.